All right, let's talk about the quantum internet. You've probably heard this term thrown around, right? It sounds like something straight out of a sci-fi movie. But what is it actually, beyond all the hype and the crazy headlines? Well, that's exactly what we're going to break down right now.
So, the very first thing people think of when they hear quantum is speed. Blazing, unbelievable speed. And the biggest claim you'll see is that this new quantum internet is going to be like 1,000 times faster than what we have today. So, are we talking about instantaneous downloads? Is that what this is all about?
Let me just be as clear as possible right up front. No, absolutely not. That is the single biggest myth, and we have to get it out of the way. Look, quantum mechanics is weird and amazing, for sure, but it doesn't break the ultimate speed limit of the universe, which is the speed of light. You just can't send information faster than that. So this network, it's not about making your Netflix buffer faster. Its purpose is something else entirely. So let's officially put that idea to rest. We're going to start by debunking this biggest myth.
This quote really just hits the nail on the head. The real excitement here isn't about faster-than-light web browsing. It's about security and about whole new capabilities that are literally impossible on the internet we use every single day. So the real question we should be asking is, what are those new capabilities?
And that brings us perfectly to our next section, a new kind of network. Because if the whole point isn't speed, then what is it? This is where it gets really, really interesting. Because we're not just talking about an upgrade here. We're talking about a fundamentally new type of network.
So here's the core of it. The quantum internet is a network built to send and manipulate quantum information, these weird properties like entanglement, between two different places. So instead of sending regular bits, the zeros and ones that make up your emails and photos, it's designed to distribute these incredibly fragile but also incredibly powerful quantum states to do jobs our classical internet just can't handle. This table really lays out the differences perfectly. Our classical internet, it runs on bits. You can copy them 1 billion times, no problem. The quantum internet uses qubits and entanglement. And here's the kicker. Because of a rule in physics called the no-cloning theorem, you actually cannot perfectly copy an unknown quantum state. And that has massive, massive implications. It means you can shift from security based on math problems, which could one day be broken, to security based on the fundamental laws of physics.
And this leads to a super important point. The quantum internet is not going to replace the one you're using right now. It's an augmentation. A really good way to think about it is this. The classical internet is like our massive public highway system, carrying all the cars, trucks, and normal traffic. The quantum internet? That's more like a super secure, specialized courier service with armored trucks built for moving one-of-a-kind, priceless packages. They're going to work side by side.
Okay, so how does this whole thing actually work? Let's take a quick look at the building blocks. And don't worry, I promise this isn't going to turn into a deep, complicated physics lecture. We're just going to cover the basics. It really boils down to 3 key pieces of hardware. First, you need something that can generate pairs of entangled photons. That's your source. Second, you need something called quantum memories, which are basically little holding pens to store these super fragile qubits for a little while. And third, and this is the really tricky one, to send information over long distances, you need quantum repeaters to extend the range.
And all this leads to one of the most mind-bending ideas in all of physics, quantum teleportation. Now hold on, this isn't Star Trek. We are not beaming people around. What we're doing is moving information, the exact quantum state of a particle, from one location to another, without physically moving the particle itself. But look closely at step 3. To complete the teleportation, Alice has to send Bob some regular information over the good old classical internet. And that's the proof right there. No information is actually traveling faster than light.
So now that we have a bit of an idea of how it's built, let's get to the best part. The real quantum revolution. What can we actually do with this thing? What does it unlock? This is where the true potential really starts to show. The number one application, the one everyone talks about, is unhackable communications. It uses a technique called quantum key distribution, or QKD. Basically, it allows 2 people to create a secret encryption key knowing with 100% certainty that no one else has it. How? Because if a spy tries to intercept and measure the quantum particles, the very act of looking at them changes them. The eavesdropping is instantly revealed. It's security that's literally guaranteed by the laws of physics.
What's next? Well, how about a global quantum computer? Instead of trying to build one single, unimaginably complex quantum computer, you could use the quantum internet to link together lots of smaller, more stable ones. By sharing entanglement between them, they could all work together as one massive, distributed machine, powerful enough to solve problems we can't even begin to tackle today.
And it doesn't stop there.
Think about sensors. By linking things like atomic clocks or telescopes or even gravity detectors together with quantum entanglement, you can get a level of precision and synchronization that's just physically impossible with classical tech. This could completely revolutionize everything from GPS navigation and medical imaging to fundamental scientific discoveries.
Okay, I know, this all sounds incredible. It also probably sounds like it's 100 years away. So, what's the real story? When can we actually expect to see this stuff in action? Let's ground ourselves with a realistic timeline. First off, we have to acknowledge that this is hard, incredibly hard. There are some huge challenges to solve. For one, qubits are super fragile and get lost easily in today's fiber optic cables. The quantum states themselves also tend to just fall apart or decohere in tiny fractions of a second. And those quantum repeaters we need for long distances, they're still basically in the prototype stage.
Because of those challenges, this rollout is going to be gradual. In fact, you could say it's already started. Right now, there are small, city-sized quantum networks connecting banks and labs for super secure communications. In the next decade or so, we'll probably see those start to link up into regional backbones. But a full global quantum internet? Well, that's a multi-decade effort. Kind of like how it took decades to build the classical internet we all know and love today.
So that brings us to the final thought. The quantum internet was never about speed. It's about building a new foundation for communication, for computing, and for sensing, one that's built on the fundamental laws of the universe. It's a huge, long-term project, but when you think about what it could enable, it leaves us with a pretty big question. Is an unhackable internet worth the wait?